Hi, and welcome to our talk on intersection-free rigid body dynamics. My name is Zachary Ferguson, and this is a joint work with Minchen, Teseo, Schneider, Francisca, Gil-Ureta, Timothy Langlois, Chenfanfu, Jiang, Denis, Zorin, Denis, Kaufman, and Daniele Panozzo. We introduced the first implicit time-stepping algorithm for rigid body dynamics with contact and friction that guarantees intersection-free configurations at every step. With few degrees of freedom, rigid bodies are useful for applications where the deformation is negligible, such as games and robotics. In robotics, it is common to use rigid simulation with reinforcement learning. Here, for example, a robot learns to walk through thousands of simulations using NVIDIA's physics engine. Let's start by reviewing methods for rigid body collision handling. State-of-the-art methods take a full time step, seeking to resolve all collisions simultaneously. In doing so, they can be efficient and take large time steps, but often fail to resolve all intersections. How well they do per simulation depends on parameter choices. Our goal is to address these problems by introducing a method for rigid bodies that is reliable, stable, and intersection-free at every step. Furthermore, these guarantees should be independent of the geometry or parameter choices. This comes at a computational cost, but our method is fully automatic and does not require parameter tuning. How can we achieve these goals? One possible solution is to use an explicit method. Explicit methods step the system of rigid bodies up to each next time of contact, then process the collisions and repeat. To do so, time steps can become arbitrarily small as collisions become frequent, and so simulations can be impractical to run. Instead, we propose a method based on a recent work in deformables, incremental potential contact, IPC. Where similar to state-of-the-art methods, we step all bodies together but disallow any intersections through the use of a barrier potential and continuous collision detection. Every substep is intersection-free, so the end result will be intersection-free. This allows us to take large time steps and provide intersection-free guarantees. As I said, we propose to achieve our goals by extending our previous work, incremental potential contact. IPC is capable of handling collisions without parameter tuning and guarantees intersection-free configurations at every step. Our original work was tailored towards deformables, so here we will work to extend IPC to rigid trajectories. We can easily simulate different mechanisms. For example, this piston features tight gaps that pose no problem for our method. This bike chain is particularly interesting as each link is realistically composed of links and bearings. There is no need for articulated constraints. An application of our work is the virtual testing of mechanical parts before manufacture. We download the parts and directly simulate them. You can see as the key turns, this causes the pins to be pulled in by the curved path in the middle. When the pins are completely pulled in, the box is unlocked and the bottom is free to fall under gravity. We can also simulate the classic friction benchmarks of an arch and a card house. For added difficulty, we use codimensional cards where each card is composed of only two triangles. Another great example of frictional dynamics is a spooling coin, both spinning and rolling. We nicely capture the expected behavior. Our work is the first fully implicit method for rigid bodies with contact which guarantees non-intersection. It is robust and accurate with no parameter tuning, guarantees intersection-free configurations at every step, and is capable of taking large time steps. To do this, we propose a novel curve CCD that can be applied to any nonlinear trajectories. In the future, it will be important to look at performance to match the expected speed of other methods. While our method can exhibit restitutive behaviors due to the barrier potential, it is largely uncontrolled and dependent on the time integrator. Controlling restitution is an important piece to work on in the future. Adding support for articulated bodies presents a nice avenue for improved performance and are useful for applications in robotics. Lastly, a benefit of extending IPC is that we can easily unify the original deformable formulation with our new rigid one. To find out more information, you can find the links to our paper, videos, code, and data on our project website. Thanks for watching.